Hello guys, this time I will be demonstrating to you numerical methods in solving ordinary differential equations. The methods used for solving ordinary differential equations are the Euler's method, the midpoint method, the Young's method, the Ralston's method, and the RK4 method or Wunsch-Kutta-4 method. So, before we solve ordinary differential equations, let us define first what are ODEs. So ODEs are equations that represents the relationship of variables y and x, or the dependent and the independent variables. These relationships are represented by a constant rate of change of the dependent variable with respect to the independent variable. So these are equations that don't show a direct relationship of variables but possesses initial states or values. So for example, let us define first what the Euler method is. So in Euler method, as you can see on this graph, so this is the Cartesian plane having the y and x axis, and for example we have a function defined as f of x. So if this is an ordinary equation, differential equation, so in ordinary differential equation we have what they call the derivative or differential variable. So for example, we have an equation dy over dx equal to the function at x1 and y1 in initial states. So given this function and we have an initial values or initial states at xi and yi, we are to define it or predict the value at the next state or next step size or next value of x. We are to predict the y value or the function value at that point. So as we can recall, in Euler's method we are given dy over dx equal to f of xi and yi. We know that dy over dx is the slope of the tangent line. So given the equation, we can substitute the dy over dx to its slope form, or the approximation value, which is y1 plus I minus y1, or simply this is the rise. So you can see on the graph, it is the change in y, and then x1 plus I minus xi, or simply the change in x. So change in x, if we are to draw a line there, that would be draw a line from yi to yi plus 1 on the function. Then we are to have an approximated slope of the tangent line, or the dy over dx. So in Euler's method, the formula for getting the approximated value or the prediction of our next state of function y will be equal to so you're just going to cross multiply this to the other side, then transpose the other I. So the formula will be yi plus 1 equals to y initial plus the function at xi yi times xi plus 1 minus xi, or simply the step size or difference in the x values. So if we are to have a smaller h or step size, we are to have a more precise data of our next I. So now here are the different numerical methods I am to discuss to you. So first one is the Euler's method, which I have already discussed the formula for getting the next y value. Now for midpoint method, you are to memorize the number 1/2, which is then in every method for midpoint, Ralston, and Newton's, we are to have two constants. We are to solve two constants. So as you can see, we have K1 and K2 there, and K1 and K2, then K1 and K2. So for K1, for the three methods, midpoint, Ralston, and Newton's, the equation is the same. So K1 is simply equal to the function or the function value at xi and yi, or at initial values. So the K1 for midpoint, Ralston, and Newton's are or is the function value at initial states. Then for K2, we are to get the function value at xi plus 1/2 of h, or the half of the step size, and at initial state of y plus half of our step size times our K1, or the first value we solved at K1 here. And then the equation for getting the approximated y value of the differential equation will be equal to, so yi plus 1 equals y initial plus K2h. So now for Ralston method, our K1 is the same for midpoint, and then our K2 will be the function value at initial x plus 3/4 of h. So notice in midpoint we use 1/2. Now for Ralston, we are to use 3/4. So the same with the initial state at y, 3/4 K1 plus h. So our K1 will be substituted here. And then for our next value of y, that will be y1 plus 1, or yi plus 1 initial state, equals to y initial plus the 1/3 of K1 plus 2/3 of K2 multiplied to the step size. Unlike midpoint, we only use the K2 here, but here we used 1/3 of K1 and then 2/3 of K2. Now for Hion's method, the K1 is the same for Ralston and midpoint, but for K2 we are to get the function value at initial x plus the step size, and then initial y plus K1 times step size. So if in midpoint we use 1/2 and then Ralston we use 3/4, in Hion's we are to use the whole step size. We are to add the one whole step size at the initial states, and then substitute it to the function. And then for our approximated y value, or next y, that will be equal to y initial plus 1/2 of K1 plus 1/2 of K2, quantity multiplied to h. Now for our RK4, or Runge-Kutta method 4, we are to have simply stated four variables or four constant values. These are the K1, K2, K3, and K4. Now for K1, it is the same for midpoint, Ralston, and Hion's. But for K2, we are to use the K2 of midpoint, which is x1, the function value at x1 plus 1 of h, and initial value of y plus 1 of K1 plus h. Now for K3, it has the same equation as K2, but the K1 here in K2 will be replaced by K2 itself. So xi plus 1 half h, and at initial y plus 1 half k2h. Now for our k4, it will be the function value at x initial plus the whole step size, and at initial I or y value plus k3, so k3 will be substituted here, times the step size. So the final equation for getting the next y value will be y initial plus 1/6 of the quantity summation of k1 plus 2k2 plus 2k3 plus k4 times quantity to the step size. Now, let's proceed to the examples. Now, for our example, we have the equation dy over dx, which is a differential, equals to 3e raised to negative x minus 0.4y. So as you can see, on the right side we have x and y. So initially, ry, given at x equals 0, ry value will be equal to 5. Now, find y at x equals 3 using h equals 1.5 and h equals 3. So in solving this differential equation, its true value will be at y3 is 2.763. So for Euler's method, if we use h equals 3, our y of 3 will be equal to, so let's, as you can see on the equation or the formula for getting the next y, is equal to the y initial plus f of x initial and y initial multiplied to the step size. So for a step size of 3, we will only be having one equation. So it is y of 3 equals to y of 0 plus f of initial x, which is 0, and initial y, which is 5, times the step size, which is 3. Then substituting that, it will be equal to, so y of 0 is 5 given, then plus the equation, substituting 0 and 5 to the equation, so 0 and 5, so 3e raised to negative of x, which is 0, minus 0.4 times y initial, which is 5, multiplied to the step size 3. So the answer in that will be 8. So as you can see, its relative true error is equal to negative 5.237. So that is solved using 2.763 minus 8. So let's try using 1.5 step size. So as you go to y of 3, you need to get first to y of 1.5. So from y of 0 to 1.5, that will be y of 1.5 is equal to initial of y, which is 0, y of 0, plus f of 0 and 5 multiplied to step size of 1.5. That will be equal to 5 plus the equation, substitute 0 and 5, e raised to negative 0 minus 0.4 times 5, quantity multiplied to the step size 1.5. You'll have an answer of 6.5. And then this 6.5 will be your next initial value of y to be substituted to the next equation, which is y of 3 is equal to our initial y, which will be now 6.5, plus f of the initial x and initial y, which wherein the initial x is 1.5 and the initial y now is 6.5. So 1.5 and 6.5 multiplied to a step size of 1.5. That will be equal to 6.5 plus quantity. Now substitute the initial values. So 3 e raised to negative 1.5 minus 0.4 times 6.5. Quantity multiplied to 1.5 step size. The answer will be 3.604. As you can see, this is more precise than having a step size of 3, which results to 8. So the relative true error of this one is negative 0.84108. So let's try this example problem to the other method. Now let's see using the midpoint method. So as you can see, on the midpoint method, we have the equation. We'll need to look for the variables k1 and k2. So k1, as you can see, the function value at initial values of x and y, and then our k2, function values at our x and y, but you are going to add half of the step size on each. So let's see. So for our k1, which is of our function at 0 and 5, which will be equal to 3 e raised to 0 minus 0.4 times 5, that will be equal to 1. So for our k2, that is a function value at 0 plus 1 half of step size, which is 3 over 2, which is equal to 1.5. Now, what we used here as h is 3. So 1.5, although 3 over 2 is 1.5. Then 5 plus half of step size, as said in here, so we'll be using 1.5 times the k1, which is 1, so we'll be using 1 here, and then substituting that to the function. So 3e raised to negative 1.5 minus 0.4 times 5 plus 1.5. The answer for that will be negative 1.9306. Now for getting the next y value, or at y3, we'll be using y initial plus k2 times h. So y initial, which is 5, plus k2 3. So 5 plus k2, which is 1.9306, times the step size 3. So the answer for that will be negative 0.7918. So as you can see, its relative true error is 2.763 minus negative 0.7918 equals 3.5548. So as you can see, the 3.5538 here, 48 here, relative true error is much smaller than the relative true error in Euler's method for having a step size of 3, which is negative 5.237. That is much larger than 3.5548. So as you can see, if we use a smaller step size in using midpoint method, we may have a smaller relative true error in relative true error for that. So let's proceed using h equals or step size of 3, but using Ralston method. So if you can see, Ralston method as a function k1, so we need to get the values of the constants k1 and k2. So k1 is the same for midpoint, so that will be equal to, as you can see here, that's 1, so we'll be using 1 as k1. Then for k2, the equation will be, as you can see, function value at initial plus 3/4 of h, and then initial of y plus 3/4 of h times k1. So that will be function value at 0 plus 3/4 of step size and 5 initial value plus 3/4 of h times k1, which is 1. So substituting that, this will be 9/4, then this will be 5 plus 9/4. So 3 e raised to negative 9/4 minus 0.4 times 5 plus 9/4. The answer for that will be negative 2.5838. Now, for getting the y at 3, we'll be using y1 or y initial plus 1/3 of k1 plus 2/3 of k2 multiplied to the step size. So we'll be using y initial plus 1/3 of k1, which is 1, plus 2/3 of k2, which is negative 2.5838, times the step size 3. So our answer for that will be 0.8324. So as you can see, the relative true error of this one is 2.763 minus 0.8324, 1.9306. Again, this is more accurate or more precise than the midpoint method. So let's proceed for the NuMeths method. So in NuMeths method, as you can see, the K1 here is the same for Ralston and for midpoint. So our K1 again is 1. And then for our K2, so you can see on the equation, initial value of x plus step size, and then initial value of y plus step size times your K1. So as you can see there, function value at 0 plus 3 and 5 plus 3 times 1. So substituting that, 3e raised to negative 3 minus 0.4 times 8. So the value for our K2 will be negative 3.0506. Now, substituting that to our equation for getting the value of our next y, or at y03, it will be equal to y1 plus, or y initial plus 1 half of K1 plus 1 half of K2 multiplied to our step size. The answer for that will be, so 5 initial y plus 1 half of K1, which is 1, plus 1 half of K2, which is negative 3.0506, multiplied quantity to the step size 3. Now the answer for that will be 1.9240. So its relative true error will be 2.763 minus 1.240 which is 0.839. Now compared to Ralston method, which we have a relative true error of 1.9306, NuMeths method is much better, which is a relative true error of 0.38, much closer to our true value. Now for our K4 method, we are going to solve 4 constant values. So K1 is the same for the other 3 methods for the midpoint, Ralston, and NuMeths. So that will be equal to 1. Now for our K2, which is the same as the K2 of midpoint. So as you can see, our midpoint on our solution is K2, as you can see here, that is negative 1.9306. so stated there, negative 1.9306. And then for our K3, we'll be having the same equation as K2, but we'll be multiplying K2 on the step size to be added to the initial value of y. So that will be K3 equals to the function value at x initial plus 3 halves, or that is the half of the step size, and initial value of y 5 plus 3 halves, or half of the step size, multiplied to the K2, which is negative 1.9306. When you substitute that to the equation, what you'll get is negative 0.1722. Now for our K4, the equation will be function value at initial x plus a step size, then function value at y, the initial value of our y plus K3. So K3 will be using the value of K3 here multiplied to the step size. So K4 is equal to 0 plus 3, 0 3, or initial value of our x plus 3, and then for the initial value of y 5 plus negative 0.1722, that is the K3 multiplied to our step size. So substituting that function of the equation, the values of x and y to the function, we'll have a value of negative 1.83 for our K4. Now for our y3, the equation is initial value of y plus 1/6 of the quantity summation of K1 plus 2K2 plus 2K3 plus K4 multiplied to the step size. So you will be having 5 plus 1/6 of K1, which is 1, then 2 times K2, which is negative 1.9306, plus 2 times K3, which is negative 1.722. So plus our K4, which is negative 1.83. Then multiply that to quantity to our step size, which is 3. Now, the answer for that will be 2.4822. Notice that the true error of this value will be 2.763 minus 2.4822. The answer is 0.2808. So as you can see, RK4 method is the one that gives the most precise value of for the solution of our differential equation. So as you can see, just using a step size of 3 gives us a very precise method. So if you use a smaller step size, you might have, or you will have, more precise or more accurate value of our solution for y. So you'll have a smaller true error or relative true error here. So that's for the ordinary differential equation numerical methods, the Euler's method, the midpoint method, the Ralston, the Yunus, and the RK4. So thank you for listening. That's all.